We had just gotten that the effective width for calculating moment capacity was 60 inches. We also were guessing the size as 24 by 16, which is 20 inches below the slab. And now we're going to calculate the moment. This right here is that right there is the slab self-weight. Okay, this part here is 50 PSF. We did that for the slab design, 1/3 deep times 0.15 kips per cubic foot for concrete. And the tributary width of this beam is 10 feet. Let me go get that picture. Right? Here it is. Oh, didn't work out. Anyway, these are at 10 feet. And so the tributary width is 5 feet on either side, or 10 feet. So that's this. Okay, the weight of the beam, we talked about this. Here's this picture. We estimated 24 inches for H. So the additional weight, in addition to the slab, is 20 inches below the slab, 16 inches wide. So the self-weight of the beam is 20 inches below the slab times 16 inches, changed to square feet, divided by 144, and the unit weight of concrete again is 0.15 kips per cubic foot. And this all comes out to 0.83 kips per foot. And the total dead load was the 175 PSF. So divide by 1,000 to get KSF. Tributary width of 10 feet. And the beam itself weighs 0.83 kips per foot. And when you add that all up, you get a dead load of 2.58. So remember, so this has everything: the slab, the beam, and the dead load. The live load was coincidentally 0.15 KSF. It has nothing to do with the 0.15 kips per cubic foot that concrete weighs. And again, the tributary width of 10 feet, 1.5 kips per foot. And you factor 1.2 dead, 1.6 live. And this is the W we'll use on our beam for the structural analysis, 5.5 kips per foot. Okay, and so here is the true moment diagram for this. This moment here is WL squared over 8. And this moment here, according to this table, is 9 over 128 WL squared. I'll confess, when I first did this example, I didn't have this. I had some paper and pencil. And what I ended up using instead of that was WL squared over 16. And let me show you where I got that real quick. So this is where I got the WL squared over 16. And there we go. This is also an advertisement for you in my University of Wyoming class to take Structural Analysis 2, Indeterminate Structures. So that'll be fun. 3, 6, 9, 7. That's L. That's W. And I did some quick moment distribution. And so you're gonna have to take that class to learn this. You put in some fixed and moments, WL squared over 12. And so you really won't understand this until you take 4200, but this gives you an example of how I do things and why you could do this. Oh, see, I already messed up. Plus, minus, plus, minus. You add it all up, and you get 0, negative 3 WL squared over 24, 3 WL squared over 24, and 0. And this is how I knew, and these are technically exact. So I knew this to start with. I actually didn't even do this on paper. I did that in my head. I knew it was WL squared over 8 in the middle. And that agrees with that chart we just looked at. What I want to show you is how I came up with the WL squared over 16. Okay, so let me do this again. Let's see, we're going from here to here. I'm having trouble with my glasses. Okay, so we're going this far. Okay. I knew that in the middle, this moment was WL squared over 8 by what I just showed you up there. So I didn't actually even do that. I did that in my head. I just visualized that. Okay, so I knew this is what we're starting with. WL squared over 8 in the middle. And I knew I wasn't going to get the maximum moment, but the moment in the middle of the spans was going to be close. And by similar triangles, I knew that was going to be WL squared over 16. And then I knew, we talked about this total static moment. You add WL squared over 8 to that. And I knew that was going to end up at WL squared over 16 in the middle. And that's how I used that number. And then I also knew that this slope was parallel to this slope, and I knew it was going to be slightly higher to the left of that, but I called it good, and I used that. The real moment was 9 over 128 WL squared over 15, and it doesn't happen at the midspan. It happens at I can't see that. This is too small for me. I think that's 3/8L, not 4/8L. But you know, 1/16 is 8 over 128. That's super close to 9 over 120. I didn't know it at the time. I just knew that 1/16 was going to be very close to the true maximum moment. And so this whole example that I'm about to do, I actually used WL squared over 16 as a positive moment instead of, I used 1/16 instead of 9 over 128. And I know that's going to cause some of you grief, but let me show you without even knowing the kinds of approximations we're making. This reaction here is 3/8 WL. And that makes this middle one 5/8 times 2, so 10/8 WL. And we don't even think twice about using tributary widths to assign loads to neighboring parallel beams. And if we use tributary widths, we would use 1/2 WL on the two outside reactions and WL in the middle. And we wouldn't even think twice about that. Whereas the real answers are 10/8 and 3/8. This error gets smaller and smaller as you have more spans, but I'm just saying that I'm not gonna sweat using 1/16 instead of 9/128. That's just one example. Here's another one. In my class last semester, we broke a dozen cylinders every week for 4 weeks for 3 different water cement ratios. And this is a box plot of the range of strengths we got for the concrete strength. That's like, I don't know, that's like 750 PSI range, right? 700 to 800 PSI range in the compressive strength. I am not gonna worry about using 1/16 instead of 9/128. And I didn't want to redo all these slides. So I'm going to continue. Again, I use WL squared over 8 for those and WL squared over 16 for these. And it was nice. I could just take the negative moments and divide by 2. It also was super handy. Okay, you get those dead loads we computed. You do WL squared over 8, WL squared over 16. Get the live load, W squared over 8, WL squared over 16. You factor those, 1.2 dead, 1.6 live, and you get these. That's negative moment and positive moment. The next was to pick a percentage of steel and 4 and 60, halfway between rho min and rho max is 1.07%, and you put that into the fancy rho and Rn equation and you get 0.581 KSI. And so this is a key thing there. I'm going to use 0.581 KSI. Now, sizing the beam. The negative moment is bigger, so we're going to use that. But even if it wasn't, okay, you've got this beam that looks something like this. Oh, this is not coming out very nice. Anyway, this is 60 inches wide on the top, and for now, I think I was guessing 12 inches wide on the bottom. And so under positive moment, this is in compression. And under negative moment, this is in compression. Let me do a different color for negative. And for negative moment, this is going to be in compression. Okay. A T-beam is much more efficient in positive moment than negative moment. We want to size it for its most inefficient function. So we're going to design it for the negative moment. And on top of that, the negative moment was bigger. We're going to size it using the small width. Here we go. And we're going to use it with Rn is 581 PSI. The negative moment over phi, changing the kip inches, was 3.667. And so you take 360.67 over 0.581. And you need this, okay? And then I did B times 1.5 B. We've done this a lot of times. Okay, so this is why we're doing the negative moment. If it was a positive moment, the D is actually less than the B, right? So the D is 24 inches and the width is 60 inches. It doesn't make any sense. So we're doing this for the negative moment. In the negative moment, it's a rectangle. And I get 14.1 instead of 12, so I picked 14. Now, we should then go all the way back to, where's the slab? Oh, way, 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 way back up here. Nope. Here. Where did I do that? When I got this, that was assuming the width of the beams are 12 inches. It's actually less now. It's like 2 inches less. I'm not gonna redo it. I'm gonna keep the slab design. I'm not gonna redo this. Okay, so back to what we're doing. Okay, so we got the moments, and now we're sizing the beam with that, and we've got 14 instead of 12. And then I did 14d squared equals 6310. I solved for d, and it came out to 21.2. By now I figured out if I can round d to a ½ inch, when I add 2.5, h will come out nice. And so d is 21.5. I add 2.5, and h is 24, like I guessed. So it's 14 by 24, not 12 by 24. Okay, and this is our final pick. But this 24 inches includes the 4-inch slab. Therefore, it's only 20 inches below the slab, and the self-weight is 20 times 14 divided by 144 times 0.15, 0.29 kips per foot. Update the self-weight. Okay, because you got this 0.29. I'll skip all the details, and we get these new MUs with the updated moments. Okay, next we're going to calculate area of steel. I'll do that in another video. This one's getting long.